So now we will solve this problem. Falling film on vertical plate, that is, there is a plate of length L and width W over which a film is falling of thickness delta. We will solve this problem using equation of change approach. So now for equation of change approach, we have a total of 45 equations from which we have to choose a single equation. So first of all, Vx is equal to 0, Vy is equal to 0 as there is laminar flow. Vz is not a function of y because end effects are negligible, and Vz is not a function of z because due to mass conservation and the film doesn't get thinner or thicker. So Vz is only function of x and pressure is function of z. So as we have assumed that there is constant density and viscosity system, we are brought down to 9 equations which are of Navier-Stokes, and from that we will have to only select z direction momentum equation, which is z direction momentum equation is written over here, and in this, as there is steady state, this terms become 0. Then Vx is 0, this term becomes 0, Vy is 0, this term becomes 0, Vz is not function of z, this term becomes 0, again this term will not be 0, this term is 0 as Vz is not function of y, Vz is not function of z. So we are remained with only these three terms, 1, 2, 3. Writing this equation here, we get this equation. So the pressure gradient is also due to the surrounding air. So this we have proved earlier in shell balance approach that dou P by dou Z is equal to rho air into G. Substituting this equation here in this equation, we get rho minus rho air. And as rho is of liquid, it is much greater than rho of air. So rho minus rho of air we can say is approximately equal to rho. So substituting this again in this equation, we get this equation, which is a final velocity differential equation. Integrating this once yields this equation. Again, integrating it, we get this equation. And now applying the boundary conditions at x equal to 0, dou Vz by dou x is equal to 0, gives us C1 is equal to 0. So this term again cancels. Then applying x equal to delta and Vz equal to 0, we get the value of C2. Substituting that value of C2 in this equation, we get the velocity profile. And again, we know Vz is equal to minus mu dou Vz by dou x. So just differentiating Vz with respect to x, we get moment of flux profile. For maximum velocity, we just have to put x equal to 0 in this velocity profile. We will get maximum velocity profile. For volumetric flow rate, what we have to do is just yes, we have to integrate twice the velocity profile on over which the flow is flowing. This is our flow area W delta. So integrating it with x and y, we get final volumetric flow equation. And we also know that volumetric flow equation, average velocity is equal to volumetric flow rate upon the flow area, which is W delta. So dividing this volumetric flow rate by flow area W into delta, we get the average velocity relation. So now there are some numerical based on this. So this is numerical 1. Water at 20 degrees Celsius is flowing down a vertical wall with Reynolds number 10. Calculate the flow rate in gallons per hour per foot of wall width and the film thickness in inches. So we are given the properties of water at 20 degrees Celsius: density, kinematic viscosity, and acceleration due to gravity. So for a falling film down a vertical wall, in Reynolds number the diameter we use is hydraulic diameter, which is expressed as 4 times the thickness of the film that is flowing over the plate. So our Reynolds number is given as rho Vd by mu. rho v d by mu. So here this diameter is hydraulic diameter, which is equal to 4 delta. Now substituting all the values which we are given above, we get the flow rate, volumetric flow rate per unit width of the wall. So now in question it is asked to calculate it in gallon per hour per feet. So here are some unit conversion. First convert it to feet square per second, then gallon per second per feet, and then gallon per hour feet. So we get 0.727 gallon per hour per feet, the volumetric flow rate of the film or the plate. So now finding the film thickness, here again we have the volumetric flow rate. So dividing just the volumetric flow rate with W, volumetric flow rate is Q upon W, so we have to get delta. So for this we use this equation, and from that we get the value of delta. Substituting all the equation value again, we have the q dash value from here we have calculated earlier. We get in meters, converting this to inches. At question it is asked in inches. So the film thickness is approximately 0.00361 inches. The second numerical on this same topic is an oil with a density of 80 kg per meter cube and dynamic viscosity of 0.05 pascal second flows steadily down a vertical wall under the influence of gravity. If the measured thickness of the liquid film is 1.5 mm, calculate maximum velocity of film, average velocity of film, and mass flow rate per unit width of the wall. So here again maximum velocity formula we have derived earlier, which is Vmax equal to rho g del square upon 2 mu. We are given the density, gravity. Density is given here 880 kg per meter cube. Gravity we know 9.81 meter per second square. Delta is given 1.5 mm. First convert into meter, then put it. And the viscosity is also given 0.05 pascal second. Substituting all the values, we get Vmax value. And as we have derived earlier that average velocity is two-thirds of the Vmax for this particular case, we can directly calculate average velocity using this Vmax value, which comes out to be 0.1295 meter per second. Then again for mass flow rate per unit width of the wall, we know mass flow rate is velocity into density into the thickness of the film. So we know the density 880. We just calculated the average velocity 0.1295, and the thickness of the film is already given. So substituting all this value, we get mass flow rate per unit width of the wall to be 0.1709 kg per meter square second.